class. I'm excited to see everyone. And today we're going to begin our next unit. It's about 2 weeks long on electromagnetic radiation and spectrum and how visible and invisible light would interact with matter. And for today's lesson, we have a funny name, espousing electromagnetic radiation. Why would we do that? Because we need to get comfortable with interaction of light with matter, and because light can interact with us, and how can we benefit from its interaction in our daily lives. And of course, we have a science standard, and it really tells in scientific terms what I have just stated. And don't matter about scientific terms for now, because later today we are going to define them for you. So the agenda for today, we're going to do 3 things. First, we're going to watch a little demonstration of how light interacts with matter, and particularly with stuff that we can drink. Also, we're going to collaboratively work on the worksheet that I have just given to you yesterday, and we're going to reflect on learning. So before we will plunge into details, let me show you a little demonstration. So I have 2 bottles. One of the bottles contains Kroger drink water with particular chemical, and another bottle is just plain drinking water. And I have an ultraviolet lamp. I will turn it on and we'll all see what will happen. If I can, somebody have to turn off the light for me. Thank you, Zach. Okay, here's the lamp. It consists of 2 types of radiation, visible and invisible. And let's take this bottle. Nothing happens, it doesn't glow, because it doesn't have a special chemical that can interact with invisible light. You see the difference? Why would it do this? Because this water contains a chemical called quinine, and we'll later learn what that is and why it glows. So you see how water and special chemicals can interact with invisible light? And it's stuff that we drink every day. That's called the tonic water. Okay. We of course have 2 learning targets for today. And the first learning target says that we can define a type of electromagnetic radiation based first on its source, on its wavelength, and on its frequency. And of course, we want to locate it and be able to locate it on electromagnetic spectrum. And a second learning target says that we can compare types of electromagnetic radiation based on their wavelengths and frequencies and identify their typical uses for our benefits, of course, because we're espousing. So let us define first scientific term, wavelength. Wavelength is denoted by Greek letter lambda, and if you imagine a wavelength, the wavelength refers to the distance between any 2 corresponding or identical points on a wave. You see, this is the wavelength, and these 2 points are identical. They're located on the crest, or wavelength should be located here on the troughs of this wave. So that's the first term. Second term is frequency, and frequency refers to the number of oscillations, or in simple term, rotations of a wave per 1 second. Think about rotations per second, not per minute, but per second. This is 1 oscillation. It refers to a complete cycle of a wave, and is denoted by the Greek letter nu. And the units for this is 1/second or hertz. Sorry about my slide. For some reason, this should be hertz, but the picture has watt. The third term is electromagnetic spectrum. And what is it? It's continuum of visible and non-visible energy. Turns out that some types of energy could be visible, some could be non-visible. And continuum here, this word refers to all possible variations of all energies available, and it doesn't matter if we can see it or not. And by the way, I still have learning targets for you, so if you did not have time to copy it down, you can still copy it or type it in your laptop. It doesn't matter what you use, as long as it's there. And of course, I have this in handout that I have just given to you yesterday, so you'll have it for your reference. And lastly, light. This is referred to electromagnetic radiation, and it turns out that light can be visible and can be non-visible. There are many non-visible things that we cannot see, and as I told you, my lamp has two types of light. First, ultraviolet light. That's why the chemical in water interacted or phosphoresced or gave off light, and visible violet light in the visible region. Now, before we're going into more details, can I have volunteers who want to define for me those 4 terms that we just talked about? Anyone? Yes, sir.
So wavelength?
Wavelength. What is wavelength?
So it's on a wave. So if you look at the wave, it's the distance between the crest of 2 waves is like a wavelength? Or
the distance between 2 corresponding points on a wave, and those 2 points can be located on 2 crests or 2 troughs or anywhere else. Let's go back to the previous slide. Right here. That's what you were referring to, and it's one of the locations of wavelengths. Who wants to define other terms? And thank you for Zoe, thank you for volunteering. That was excellent response. Who wants to volunteer? Yes, Cassie.
It was frequency, and that's how long it takes to go through a full rotation, so a full wave length.
Yes, technically oscillation per 1 second. 1 second. And that's what this slide means. That's where 1 second stands for. And yes, this is 1 oscillation or rotation of the wave. And what about electromagnetic radiation? Who wants to define this term? Anyone? If not, then let's visit the previous slide. Electromagnetic spectrum is a continuum of visible and non-visible energy. So all types of energy that possibly exist, whether they are visible or non-visible, it doesn't matter. This is what the electromagnetic spectrum refers to. And who wants to define light? What is light? Anyone? Sounds intuitive, isn't it? Okay. Light is a type of electromagnetic radiation in general terms, and again, visible and non-visible. Doesn't matter if we can see it or not. So, let me introduce one equation, and it's a rearranged form for us to be able to work on a collaborative, on a worksheet in a collaborative manner. This equation refers to the speed of light, and it has 2 components. First, a Greek letter lambda, which stands for wavelength, and mu, or frequency. So, speed of light is equal to frequency times lambda, or wavelength. And this is the and this is another version of this, or rearranged form of this equation that we are going to use. And as you can see, speed of light has an enormous value. It's very high speed, approximately 10 times to the 8th meters per second, and it's a constant. It does not depend on anything. And I have an example for you. Let us together try to solve or calculate the wavelength in nanometers. That's the units that we hopefully are familiar with. Nano is 10 to the minus 9th, very small unit. If frequency equals to, and again my slide has failed, so ideally you have your worksheet with you that I have given to you, and let's turn to the page 3 and see the example that I have for you. I think that's it.
Okay.